Hey everyone, we're always taught that prisms are basically perfect mirrors when it comes to light, but what if that's not always true? What if sometimes they just fail? Today, we're going to dive into a real physics puzzle, the prism paradox.
All right, so let's get right into it. You probably remember from science class that prisms are these amazing, total reflecting things, right? They bend and bounce light around with almost perfect precision. But here's the twist. What if, in some very specific situations, they just don't?
So before we go any further, let's do a super quick refresh on the key principle here. It's called total internal reflection, or TIR for short. Now, this is the magic that happens when light is moving through something dense, like glass, and it tries to escape into something less dense, like air. If it hits that boundary at a steep enough angle, it doesn't escape at all. Nope, it reflects completely, bouncing right back inside. And that's the whole reason prisms can act like such perfect mirrors. Okay, so to find the crack in this perfect mirror, we need to focus on one very specific character in our story, the 30-90-60 right-angled prism. Trust me, its weirdly specific geometry is the absolute key to this whole mystery. And this really brings us to the heart of the matter. We know total internal reflection should be happening. So when doesn't it? And more importantly, why does this fundamental rule of optics seem to just break? Let's dig in and find out. All right, let's start with case number one. Picture this. A single ray of light enters the prism straight on, perpendicularly through one of the shorter sides. We'll just call that face AB for now. Now, since the light ray hits that surface at a perfect 90-degree angle, it doesn't bend at all. It just zips straight through the glass until, wham, it hits that long, slanted face, the hypotenuse. This is the moment of truth, right here. Is it going to reflect or not? And thanks to the prism's special 30-60-90 shape, that light ray hits the inside of that surface at an angle of exactly 30 degrees. Okay? 30 degrees. Lock that number in your brain because it is everything. Okay, so here's the deal. For that cool total internal reflection thing to happen, the light has to hit the boundary at an angle that's greater than a certain threshold. It's called the critical angle. And for glass sitting in air, that magic number you have to beat is 42 degrees. And, Houston, we have a problem. Remember our angle, 30 degrees? Well, 30 is definitely not bigger than 42. So what happens? Poof, no reflection. The light just punches right through and escapes the prism, bending a little on its way out. That's called refraction, not reflection. Our so-called perfect mirror has completely failed us. Okay, on to case number two. What if we try a different approach? Let's send the light in through the longest side this time, the hypotenuse. Maybe that'll change things? So the light ray travels straight through to the next face, and you guessed it, the geometry of the prism works its magic again, and we end up with an angle of incidence of exactly 30 degrees. Again. So we're right back where we started. 30 degrees is still way less than the 42 we need. And so once again, the light just escapes. No reflection. It's really starting to look like this prism is a dud as a mirror. Or is it? This is where things get really, really cool. It turns out there's a loophole, a little trick, a secret way to actually force this prism to do what it's supposed to do. We can actually outsmart the geometry. And the solution is so subtle, it's almost hiding in plain sight. It's not about which face the light enters, but precisely where on that face it enters. The exact entry point is the key. Let me show you what I mean. We're going back to that long hypotenuse face. But this time, we're not just going to aim randomly. No, we've got a specific trick up our sleeve. So here's the secret. You have to aim the light ray at a very specific spot. If you shine the light so it enters the lower half of that long hypotenuse face, its path inside the prism changes dramatically. This tiny little shift in where the light goes in sets up a completely different chain of events inside. Because of this new path, when the light ray gets to the next internal face, it hits it at a much, much steeper angle. We're not talking 30 degrees anymore. Now it's a full 60 degrees. And bam, there it is. 60 degrees is finally greater than our magic number of 42 degrees. The condition is met, and we get perfect, beautiful total internal reflection. The prism can be a perfect mirror after all. So let's just quickly trace that winning path.
Step 1, the light enters the lower part of the long side. Step 2, it smacks into the next face at a nice, steep 60 degrees. Step 3, boom, total internal reflection happens. And then, steps 4 and 5, the reflected ray travels to the last face where the angle is back to 30 degrees, letting it escape cleanly. We did it. We totally outsmarted the prism's geometry. You know, this whole thing reveals a really fundamental truth about optics. The result you get isn't just about the object itself, like the prism, it's about the precise angle and position of the interaction. A tiny, tiny shift in where the light entered created a completely different outcome. It's kind of mind-blowing when you think about it.
So, what are the big takeaways here? What should you remember from all this? Well, first off, that 30-90-60 prism isn't automatically a total reflecting prism. You can't just assume it is. Second, everything hinges on whether you can beat that 42-degree critical angle. And maybe the biggest lesson of all, sometimes the most crucial factor is also the most subtle one, simply where you aim the light. And this whole paradox just goes to show you, right? Even with these rock-solid laws of physics, there are always these fascinating exceptions and loopholes hiding in plain sight. It really makes you wonder, what other rules that we take for granted have secret exceptions just waiting to be discovered? Anyway, thanks so much for digging into this with me today.